Hello, class. Okay, so today we're going to talk about heat engines and also refrigerators, kind of related to that. But the basic idea, say we have a hot object and a cold object, or just a difference in temperature. And we know heat is going to flow from hot to cold. So an example of this could be just say two different areas where one's hotter than the other. Well, we know wind is going to flow from hot to cold. So we can have wind caused by differences in temperatures. And what a heat engine does, like this is naturally going, this is an energy transfer. And what a heat engine does is it takes advantage of this difference in temperature and the energy flowing from hot to cold, and it diverts some of that energy into useful work. So we can represent this, let's say we have a hot reservoir. And a cold reservoir. And these have temperatures T hot and T cold. And again, we want to measure these in Kelvin. Now, let's say we have an engine that's going to operate between these two. So we have a heat engine. So like we have normal heat, energy is going to flow from hot to cold, but we're going to have this engine intercept that. So we're going to have something going into the engine. We're going to have heat going into the engine. We're going to call that QH. And I'm going to put absolute value signs on everything here because we have this convention where QH can be positive or negative depending on whether it's entering or leaving the system. So we want to focus just on magnitudes here. So normally we'd have energy going from hot to cold. We're going to say this energy is going into the engine, and some of that is going to be converted into work, but not all of it. We can't take all of that energy and convert it directly into work. We have to dump some of that energy into this cold reservoir. So this is like a diagram of a heat engine. And we're going to use basically just conservation of energy here. Let's look at the engine, and we can say what's going in has to come out. So we can say that QH equals W plus QC. So what's going into the engine is QH, or all these are measured in joules. And what's coming out of the engine, work, and we're dumping some energy into this cold reservoir. And so this is a very important equation for heat engines. Now let's just say as an example, say we have, now this heat engine, we want to have like a cyclic process. An example would be like an old-fashioned steam engine, where we burn coal to create a hot reservoir, and the cold reservoir is just the rest of the environment. You just dump that heat somewhere. And we get work out of it. And the goal is to get as much work out of it as possible. For a given amount, like this is the input. How much heat are we putting into, how much energy are we putting into this engine in the form of heat? And this work, that's what we get out of it. So we're going to find the efficiency So think about it. W is what we get out of it, and QH is what we put into it. And QC is basically just wasted. It would be nice if we could just erase this. Just have a heat engine take heat out of a hot reservoir and turn it directly into work. But that is not possible. It'd be nice, but It wouldn't violate conservation of energy. That's going to violate a different law of thermodynamics, which we'll talk about later, if something like that were to happen. So again, this is how we define the efficiency of an engine. And again, it's a sensible definition. Like work, that's a goal. If we get a lot of work for a given input, that's a highly efficient engine. And yeah, it's like kind of like output over input. And again, this number is always going to be between 0 and 1. Well, it can never be 1. You can never have a 100% efficient engine, but it's got to be less than 1. You can kind of approach 100% efficiency. You'll never quite get there. So E is a number between 0 and 1, and it's usually expressed as a percentage. Just multiply by 100. Okay. Now, what about a refrigerator? A refrigerator, again, normally things flow from hot to cold. So let's say you have a refrigerator, which is cold. Inside the refrigerator, the room is relatively hot. That would be the outside. And so energy wants to flow from hot to cold. So, but what we're going to do, that would heat up the refrigerator. We don't want that. So obviously we insulate it to minimize the heat flow in, but we have to continually remove heat from inside the cold reservoir and dump it into the room. And so what we're doing for a refrigerator is we're basically just reversing all of these arrows. So we're taking energy from a cold reservoir and dumping it into a hot reservoir. And again, this does not happen naturally. Heat does not naturally flow from cold to hot. We have to make it do that. And so we have to give it energy. We have to do work. So like on your refrigerator, obviously you plug it into an outlet. Otherwise it's not going to work. And so, yeah, you have to, so basically we just reverse these directions. But again, this equation is still valid. You know, what goes in is W and QC. What comes out is QH. So, yeah, heat engines and refrigerators work on the same principle. And again, we're not going into any mechanical details about, like, how this engine actually works. Like, how does a refrigerator actually work? I think I'm going to actually make a separate video with some examples of like maybe actual engines and actual refrigerators, but this is kind of just like fundamental ideas behind it. So this video will be kind of short. We're just going to focus on these fundamental ideas. But I'll post a few more things just about, yeah, more like what's actually going on in a heat engine or a refrigerator. But here we're just looking at conservation of energy, basically. And this idea that heat normally flows from hot to cold. Now, this efficiency doesn't really work for, like we want to define efficiency differently for a refrigerator than for an engine. Like here, work, we want to minimize the amount of work that we have to put into it. For a, so we're not going to call it the efficiency. For a refrigerator, we have something called the coefficient of performance. And we want to think, what is our goal? In a refrigerator, we want to take heat out of this cold reservoir. So the more we can do, the higher the coefficient of performance. So that would be QC. And the more work we have to put into it, though, the worse performing this refrigerator is. And so we're going to find coefficient of performance as QC over W. So if we have to do a lot of work to remove a certain amount of heat from inside this cold reservoir, or dividing by a big number, that's a low coefficient of performance. If we can get by with a small amount of work, that'd be a higher coefficient of performance. So again, for engines, we use efficiency. This is a number between 0 and 1. And yeah, coefficient of performance is greater than 1. So, yeah, coefficient of performance tends to be bigger numbers. Okay, now, again, this is, basically we're just looking at, the basic idea behind this heat engine. And I'm going to have separate videos, kind of more what's actually going on. But yeah, that'll be it for this one. But also another video, we're going to talk about a particular type of process. Like a particular type of engine called a kernel engine, which is extremely important. That'll be a lecture by itself. And again, it's more of this theoretical kind of engine. You don't actually build them. So that'll be a separate thing. But in the meantime, I'll find some examples of actual engines we can talk about. So again, another short topic. But we're going to continue this by talking about, we're kind of keeping this short because the one engine that we really talk about in detail is a kernel engine, and that's a whole kind of video by itself. So I'll stop this one here.